we would love to hear something about text mining and stuff like that. We started some discussions last night, but
all right. Thank you very much for the invitation. I'll get on with my presentation. Today I'll talk about multi-word term recognition, and I'll explain why that is important in text mining. So just a brief outline. I'm going to explain the importance of terms in text analysis, whether automated or manual. Then I'm going to explain what multi-word terms are and how we can extract them automatically from text. And I'll finish off with a special type of multi-word terms, which are acronyms. So, we are reading a lot. This is how we communicate information amongst each other, especially specialist information. In all sciences, we have to read papers. Often we conduct systematic reviews, content analysis, for example, interviews, transcripts from focus groups, etc. In corpus linguistics, you are observing manually how words are used, etc., etc. So all of these approaches, what's common for them is that they're data-driven. So you don't start off with a hypothesis, you are observing, and it's a data-driven approach, even though it's manual. There's lots of software support to do text analysis, like Confidence and Vivo, etc. But still, a person has to read and manually annotate things of importance in text. So there's a lot of manual labor involved. In other words, lots of reading. To speed up the reading, we use skimming and scanning. So, can you read a paper fast? How long does it take you on average?
very long.
Very long. Okay, if you want to understand every detail, if you want to see if it's good or bad, seconds. You can scan, and usually what you're looking for are the domain-specific terms, something, some theorem, hypothesis, some properties. So what are terms? Terms are linguistic representations of domain-specific concepts. I'll give you an example. I'll give you a word, and you tell me what is the first thing that comes to your mind. What is a tablet?
A pill.
Sorry, a pill. Okay. This. Anything else?
Small
it can also be this. So it is specific to a domain. If you were talking to a doctor, that would probably mean this. A computer scientist, somebody working on user-computer interaction would probably mean this by tablet. So it's domain-specific, and it's a word that actually refers to an actual concept, either abstract idea or a specific thing. So in the context of meaning, we have what we call a meaning triangle. And for mathematicians, this is not difficult. Usually, if I wrote this, like 1, what is it? Most people would say it's a number. But it's not a number, it's a representation of a number. It's a symbol. So it's the same with words. So words like rose are symbols that we use to refer to either an abstract idea of a rose as a flower, or to refer to a specific instance of that flower. So why am I talking about rose? Have you read Shakespeare, Romeo and Juliet?
Yes, of course.
Yeah, Romeo and Romeo. And I like this. What's in a name that which we call a rose by any other name would smell as sweet? So if you called the rose a tulip, a chair, or anything else, it wouldn't change the fact that it still has got the same properties. So the meaning is not in the word. We just use a word to reference that meaning. But on its own, it's got no meaning whatsoever. Okay, so when we process text, if we decide, okay, rose is a symbol that represents the idea of that flower, we can do some processing based on that. What happens when we have multiple words? So here are some examples in various scientific disciplines. Recurrent neural network is a term. It's got 3 words. Dot product is a mathematical term, stem cell fatty acid, etc. They're usually longish because we cannot come up with a new word every time, for every concept imaginable. So we use multi-word terms to describe them, so combination of different words. Because we have multiple words, they usually end up to be very long, like this one. So we can't write up this in a paper every time, so we use acronyms. as a quick reference to these multi-word terms. And it's not just any combination, it's actually very stable. So dot product, you cannot vary this. And if I say dot product to a mathematician, they will know exactly what you mean. I'll give you a few examples. So let's define a notion of collocation. So collocation is a combination of words that occur more often than would be expected by chance. So for example, you would say strong tea. So even though powerful is a synonym for strong, you would never say powerful tea. This is a powerful tea. You would say it's a strong tea, strong coffee. You discharge a patient from a hospital, but you release a person from the prison, not the other way around. So these combinations are not random. They're strongly collocated. Here's the word tall, even though you can also say high. You will say tall temperature. You say high temperature. Okay. And what happens if we separate the words? Take, for example, these idioms. So idioms are also multi-word expressions. Piece of cake. What does it mean in English? When you say it's a piece of cake?
It's easy.
It's easy, okay. If you separate it into a piece of cake and you process it separately, you lose that meaning. Imagine machine translation. So when you're translating this into some other language, have you got an expression for this as an idiom in your language? In Serbia we say simple as beans. So it doesn't sound, if you said it's a piece of cake, nobody will understand what you mean. But if you said simple as beans, it's got the same meaning. So we somehow need to preserve this combination. We can't break it down because we lose the meaning. The same as take the biscuit. To annoy somebody, not just like taking a cracker or a biscuit. So the meaning is completely different. So multi-word terms are also collocations, but they're a special type of collocations. So think of dot product. If you replace dot by period, period product wouldn't mean anything. Okay. So this is a typical collocation, dot product, but period product is meaningless. On the other hand, scalar product, which means the same as dot product, is also a valid collocation. But if you replace product by multiplication, you wouldn't get incorrect collocation. You actually also get the collocation, but it's got a completely different meaning. So you can see that you can't just pick and choose and combine any way you like. You actually need to preserve multi-word terms as they are, because they refer to a specific concept, and that meaning of that concept gets lost if you chop it up into individual words. So if we think of text representation like this, if we use multi-word expressions, we still preserve some sort of logical organization of text. If you slice it and dice it into words physically, or n-grams, you can say I'll pick 2 words or 3 words at a time, it's still physical segmentation. So in the end, you will end up retaining only surface features, and you will lose latent features. So latent feature is basically the concept that we are talking about. So if you slice it and dice it, you actually lose that latent variable. So how do we deal with multi-word terms? Can we use dictionaries and just say, okay, we have a dictionary of words, we'll run it, and we'll just keep it as a single unit in text? You can do that, and there are lots of dictionaries, scientific dictionaries, terminologies that are maintained by special professional people, but there are some problems. A lot of the domains are dynamic in nature. So computer science, new terms pop up all the time. So we can't rely on dictionaries to always be up to date. Think of medicine, swine flu. New virus, there's a mutation, suddenly it starts spreading, you need to name it, you come up with the name swine flu. All the news media start using that. It's still not in a dictionary, so you can't use it to process these references in text. On the other hand, now we have, in the era of internet, we have lots of user-generated content in media such as blogs. So lay users like patients, for example, discuss their health. Obviously for health, you use medical expressions. They're not specialists, and very often they use non-standard terminology. They will paraphrase things. So I found examples like full knee replacement. So I can get what it means, but I checked in a dictionary, this is never listed as a term. The only thing you will find is total knee replacement. Okay. So in this case, we also can't use a dictionary, but we will still want to keep this as a single unit in text. So the point is that dictionaries are not always suitable. So in many cases, they will not be either up to date or they will not contain non-standard terminology. So what is the alternative? So what we want somehow to segment the text and pick up these multi-word terms automatically without the use of any dictionary. So it's a data-driven approach. So how do we do this? We need to explore some properties that distinguish terms from other multi-word expressions in text. We can explore their syntactic structure, the way in which the words are combined, or frequency distribution, how often they are mentioned. Usually when you talk about deep learning, you will keep referring to, say, recurrent neural networks. So that's going to be mentioned many times in text. So you can rely on either linguistic properties or some statistical properties of multi-word expressions. So based on this, we can come up with two approaches. One based on tagging, where we attach lexical class to each word, and then we use pattern matching to extract only certain structures from text, or we can simply count and see how many times a multi-word expression is mentioned. So there are two early studies in terminology. So back in the 90s, Statistician and Katz used the linguistic properties, the syntactic structure, to extract multi-word terms. What they noticed was that terms were almost always noun phrases, and not just any noun phrases, but those that are combined of adjectives, nouns, possessive, and prepositions. You can describe that by regular expressions. So this is adjective noun. So either adjective or noun followed by noun. So here's an example. Mean squared error. So that's a term. You can use possessives. So here it is. This phrase matches this structure, Zipf's law, or the law of large numbers, so a combination of noun phrases with a preposition. So they use this, and they simply extracted the candidate terms and counted which ones occurred most frequently, set a threshold, and pulled out a lot of the main specific terms. Okay, but there are also other phrases that are not terms that may behave in the same way. So it would be nice to explore some statistical properties that terms may exhibit in a large corpus. I also already mentioned that multi-word terms are special types of collocations. So Kita et al. In 1994 studied the collocations, so not in relation to terms, but we'll see how this can be used to also extract terms. What they observed is that, yes, collocations are recurrent word sequences, and this recurrence here can be captured by absolute frequency. But if you use simple absolute frequency, that will not work. Why? Because every subsequence is going to have higher frequency than the longer subsequence. So it's not going to favor longer combinations of words. For example, in spite of is a collocation, but in spite will occur more frequently than this one. So you somehow want this to be higher ranked than the subphrase. So they came up with the cost criteria formula, which is actually quite simple. So the logic is that the cost of processing a multi-word phrase should be proportional to the length. So here we have the length in the number of words. It should also be proportional to the frequency. So we have frequency of alpha here, but we don't want to double count. So simply subtract the frequency of the longer phrase. And that will favor the longer one, like in spite of, which will be higher ranked using this cost criteria. Okay, so how do we now this apply to terms? So terms are collocations, they have specific structure. We can combine these two. So C-value method is a hybrid solution that combines cost criteria with linguistic filtering to extract terms. So the idea is similar. We have C-value that is proportional to the length. So you only have logarithm here, but it's still the same idea. We have frequency here, but we also have, like before, we are subtracting some frequency, but there's a slight variation. So here this set denotes every longer term candidate. So we say the term T is nested in term S, term candidate S here. So think of anterior cruciate ligament or posterior cruciate ligament. So his cruciate ligament is nested in both these two. So we want to subtract these frequencies from the frequency of cruciate ligament. But there's a catch. Okay, sometimes there will be a lot of different modifiers here. In that case, we say, well, it looks like cruciate ligament is something important. It's just modified many times, so we don't want to punish it too much because it's a standalone term on its own. So we reduce the punishment in this formula. On the other hand, if it's always nested in one term, we want to favor that term. So in that case, the punishment is the highest here because we divide only by 1. So this method, in essence, favors longer, more frequently, and more independently occurring term candidates. So this approach works well when terms are used consistently. You use them every time in the same way. However, terms do vary, so we have lots of orthographic variation. So here we have posterolateral coordinate without white space, with white space, or with hyphen. So if you have things like this, then it messes up the formula before. There's also lots of morphological variation, like lateral meniscus, plural and singular, will be different here. So we somehow need to neutralize this variation here, because if you compare these two strings, they won't match. There's also derivation, where we have different class, so we can say meniscus as a noun, or we can say meniscal tail. Again, you compare these two strings, they're different, but we would like them to match. So we need to neutralize this type of variation here. And finally, we have syntactic variation. When we have different combination of the same words, like kidney stone or stone in kidney, means the same thing. So we want to match these two phrases. As strings, they do not match. How serious is the problem? Well, it's been estimated that 1/3 of English scientific corpus accounts for term variance. So it's not just an obscure problem, it's actually a real problem. So yes, they are consistent in a way, we can recognize it, but when you consider them as strings, that messes up their processing. So when we use frequency-based term recognition methods, we need means of neutralizing this term variation. So we want to associate all term variants with one another, and when we associate them, we want to aggregate their frequencies, because then we are aggregating them at the semantic level, at the level of meaning, instead of having separate frequencies for each different variation. Okay. So back in 2013, I implemented flexiterm model method, which is based on C-value, but it takes into account this term variation phenomenon. So exactly like C-value, flexiterm will perform term recognition in 2 stages. First, we'll define lexicosyntactic pattern, and we will extract term candidates. Then we will rank these candidates using the C-value formula that will estimate how collocationally stable they are. The major difference between these two methods is the actual flexibility with which term candidates are compared to one another in an attempt to neutralize the 3 types of term variation. So flexibility here is part of the name. This is why we called it flexiterm. Okay, so how do we neutralize the variation? So first of all, we no longer treat term candidates as strings. Now we treat them as a better word. So this will solve our problem of syntactic variation because the order of words will no longer matter. We'll remove, meaningless tokens like apostrophes, numbers, and stop words. Things like preposition of or in stone and kidney, we would remove in. We will also remove any lowercase tokens with less than 2 characters, so things like possessives here, S, so you can say Alzheimer's disease or Alzheimer disease. This would solve the problem. We will also stem each remaining token, and stemming means removing the suffix, basically. So we already removed the preposition by rule number 2, and we will stamp each remaining token. So here we have hypoxia at rest, and resting hypoxia, if we remove the suffix, and we just create a bag of words, we will have the same term representative. So basically we neutralized this variation. One more thing is that with stemming, we will neutralize morphological variation. But we still haven't solved the problem of orthographic variation. So think of different spellings, like hemorrhage with A, and hemorrhage with just E here. If we stem it, these two strings will still not match. Okay, but this can be easily solved by, for example, using edit distance. So we can estimate lexical similarity, see that these two tokens are similar, set a threshold, and then just put both in the bag of words representative, and then either which you use, when we use the subset relation in the C-value formula, it won't matter anymore. We also use phonetic similarity, so something called metaphone algorithm, where we can actually, apart from lexical similarity, which means similarity of strings, we can also estimate the similarity of how words sound, so things like late or late. So this is important if you want to process non-standardized terminology. So patients, for example, they can't really spell well medication names, etc. But they will use, they will spell it in the way that it sounds. So it is important to take this into account as well. Okay, so now we neutralize that type of variation, and we now apply the formula. The difference is we no longer treat term candidates as strings, we treat them as bags of words, and because of that, the order does not matter anymore. So we solve the problem of syntactic variation. Okay, so what are the results now? Has it improved the term recognition? We tested this on 5 different corpora. So these are scientific abstracts, patient blogs, and these 2 are clinical narratives. So they all have different properties, so we have a nice range of different topics and styles in biomedicine. So first of all, we need to define what counts as correctly recognized term. So take this, for example, protein kinase C activation pathway. So if you see this in text, if you pull out activation pathway, did they make a mistake? Not really, because these are all of the terms, I put IDs here, that were pulled out of a biomedical dictionary. So protein is a term, protein kinase is a term, protein kinase C is a term, this is a term, this is a term, protein activation pathway is a term, and the whole thing is a term. So if you pull out activation pathway, yes, ideally you would like to have extracted this, but you can't really say you made a mistake. So to take this into account, we perform token level evaluation, where we effectively measure the overlap between recognized terms and those manually annotated in a corpus. And we just use traditional measures of precision, recall, and F measure. And this is slightly disappointing, because it's hiding the fact what we actually achieve with neutralizing the variation. So yes, we did fairly well on blocks, so on non-standardized terminology, and we are fairly comparable in all other corpora. We can't really see what we did without looking at the real data. So later on, I realized I shouldn't have evaluated it that way, so I will show you different evaluation that we perform, but only after I introduce additional functionality. So let's just look at the differences in what was pulled out by the original C-value method and with the new flexible term recognition. So first of all, here you have all of these different variations merged together as a single term. So if you process a text now, you can give it ID, so all of these occurrences would be treated as the same variable. We don't see that. You can see only one term on the right-hand side. Here we see patients with COPD and COPD patients grouped together. That's nice. C-value doesn't even bother with this type of structure. So it won't pull it out at all, which means, it's not risking too much. So the precision will be higher, but they will miss out on the recall because of this. However, this is where I noticed, well, ideally, these two things should be together. So COPD is an acronym for this, but they were not linked together because we were unable to link these two phrases. So COPD, in effect, is this multi-word term. So this should be together, and that may change the ranking as well. Another thing is, because this is COPD, it's a chronic disease, it's very unpleasant, and it affects the quality of life. From scientific abstracts, we managed to pull out this as a concept, quality of life, whereas Thermine, because it's not risking too much with prepositions, it ignored it completely. So if you do text mining, you can't afford to miss out on important variables such as this one. Interestingly enough, what do patients talk about COPD? Also quality of life. So that was nice to notice that the quality of life was pulled out from both scientific abstracts and from patient logs. Here we can compare these two. We can see that because of we merged all these variants, this term was ranked much higher in our approach. Data set 4 was hospital discharge summaries. There's no difference here, the first ranked term, but they missed out on this variation of the same term. And these are MRI reports, so scans of a knee. You can see here a misspelled word, meniscus, instead of meniscus. It was still pulled out as a variant of that term. And this is interesting. So orthographic variation, posterolateral corner with or without a hyphen, they were treated as different terms in C-value. Look at the ranking, 18 and 55, whereas we ranked at 11. Even worse, infrapatellar fat bed, broken down into 3 terms, so you would have 3 variables instead of 1. And look at the ranking, 14 versus 20, 281. So that's nice, but we notice the problem with acronyms. So before I show you different evaluation, I'll introduce the latest addition to Flexiterm. So what we noticed, that yes, we have orthographic, morphological, syntactic variation, but we have also lots of acronyms. Acronyms are also type of term variation because it's a different way to specify, to refer to a concept. So in acronyms, multiple words are blended into a single token, and this is where the problem begins. Acronym is a single token, single word, but in effect, it's a combination of different words. So here we have words like chronic obstructive pulmonary disease. We take the initial letter and we create a new word. But in effect, this is 4 words. This is chronic obstructive pulmonary disease. Or we have inhaled corticosteroid, ICS, 2 words, but here only 1. Again, are acronyms that important? Well, in PubMed, the largest database of biomedical abstracts, it's been estimated that there are 11,000 new acronyms in papers published each year. So they are handy proxies to refer to multi-word terms, so they should be treated as multi-word terms themselves. So this is something we didn't do before. And that actually affects the soundness of this method. So they're highly productive type of term variation. Definitely we need to take it into account. If we don't, we face the following problems. So we have this multi-word terms. We will ignore all references to this concept used by COPD. Imagine that you wanted to find information about chronic obstructive pulmonary disease, or you were just looking for word pulmonary. If you searched it in a text that used only this, you would miss that information. So we need to link this to this. So the frequency should be merged. Also, because this formula uses nestedness, this should be counted as being nested in this term. Also, this should be counted as being nested in this term. So obviously we have a problem, and that could be easily solved if we could manage to expand the term variation, the acronyms, to the full forms. Okay, so how can we do that? First, we can differentiate between two types of acronyms. So first kind is explicit or local acronyms. So this is what we use in scientific writing. So we never, students somehow, when they're inexperienced, they just start writing MDS, COPD, without defining it. Very soon the supervisor will say, you have to define an acronym the first time you use that term. So in scientific papers, we use conventions, and we usually put a bracket after the first mention of an acronym, the full form. We create an acronym, or we specify an acronym, and later on, we use this to refer to this multi-word term. So we can exploit this proximity and use some pattern matching to match this to this term, and we can resolve the problem of acronyms. However, if you focus on patient blogs, when they talk about COPD, they're not going to define it to one another. So they will just use COPD as a term. So they will not use scientific conventions. So we cannot rely on this approach. Also in clinical narratives, some doctors will use ACL, some will use anterior cruciate ligament, but they don't define acronyms for one another. Okay. So they do not follow scientific conventions, so they don't introduce acronyms, and we call these acronyms implicit or global acronyms. When it comes to explicit acronyms, there is a vast array of work done in this space. So you can pick and choose between different methods done in early 2000s. So this is what we did. We just pulled out one of the most cited paper and used their software, adopted it slightly, and we built it into Flexiter. So that problem is not that interesting. Implicit acronyms, on the other hand, are interesting. So global acronyms, the reason why they are called global, because they're also globally known. So when you say STD, most people will know that it's sexually transmitted disease. Therefore, it will be already in a dictionary. The problem is, because Flexiter is data-driven, domain-independent method, we don't want to link it to any dictionary. We want still to remain its domain independence and keep it as a data-driven approach without any references to external knowledge sources. So what can we do? For the initial experiments, we use the brute force tactic. Okay. So first of all, if you have an acronym, it will refer to multi-word term. So if somebody else uses that multi-word term, then we can actually compare that acronym not to all combinations of words in a corpus, but only to those that are likely to be terms. And this is what we are doing in Flexiter. We are already pulling out term candidates by using pattern matching. So all we need to do is extra potential acronyms based on how they look, and then just match them against existing multi-word candidates. So it was a brute force approach. It wasn't very deep, so we didn't account for all of the acronyms. But in essence, we just compared it to existing list of multi-word terms, and we said, okay, the most frequent one will be the correct resolution of an acronym. Okay, so that was solved as well. And then we just built it into Flexiter. So it didn't change much. All we did, as before, we were extracting term candidates. We extracted acronyms, processed them, found their full forms, and then expanded all references to this acronym to their full form. Once you expanded them, there's no reason why we couldn't use the rest of the Flexiter as it was. And this is what we did. So nothing changed apart from inserting this bit where we recognize acronyms and expand all references in existing term candidates. Okay, so how much did this improve the performance of Flexiter? So before we made the mistake that we actually evaluation didn't take into account that property where we conflate different term variants, and this is actually what we want to measure. So I thought about how we can evaluate this, and I just thought of an application context. So where does it matter the most, term conflation? Well, in information retrieval, it should be used for query expansion. So it's commonly expanded. So if you have one term, Google will, in the background, suggest all of the synonyms of that search term. So you don't have to think about different ways of specifying it. So the same with multi-word terms. You should only specify one when you're searching for it, but your search algorithm should expand it automatically to all equivalent phrases that mean the same thing. Okay, and we can evaluate information retrieval using precision and recall, which is what we did. And here are the results. So the major thing that we wanted to estimate here is recall. Recall means how many different variants you pulled out from text when you search for it. That means you have to manually annotate each occurrence in the corpus. That's a laborious process. Alternative is to use relative recall. So you combine all of the systems and see which one pulls out the most of the things that would be retrieved by either of the systems. So we compared the original C value, flexiterm, the original version, and the one with acronyms. And we can see in blue that relative recall improves dramatically just by introduction of acronyms. There was slight improvement before, with one exception, but this really changes things. So acronyms basically are one of the most important types of term variation. Another way to look at the problem is the term conflation. We want to see how many entries, to what extent we managed to squeeze out different term variants into a single latent variable. And we can use the index compression factor for that. So this formula is inspired by index compression factor, where we use stemming, and we see how much we managed to reduce the number of entries in a dictionary just by neutralizing this type of variation. So in our approach, instead of words, we have term variants, and instead of stems, we have distinct terms, or term representatives, and we apply the same formula. So again, we compare all the three systems, and we can see in blue that the addition of acronyms manages to conflate terms most effectively. Again, these are just graphs. Let's see what happened with the real data. So these are the results. Again, top 10 ideally, but they wouldn't fit because we compressed too many variants. Here's only top 6 on the data set in molecular biology. It's quite different to either of these. So look at this lonely guy here. Now, all of these variations are grouped together. This was nowhere near on the radar here. It's now the top ranked term. Okay, so what happened here? So this is still the same data set. We listed here the most frequent acronyms, and we want to see how they affected the term ranking. So this is the previous term rank with the original flexiterm method, and this is the new rank with the inclusion of acronyms. So we can see that everywhere it shooted up. So the ranking improved considerably. Even recall. So this wasn't registered as a term at all before, core binding factor. Suddenly, it's ranked number 10. So before that, we were blind to that term, so we couldn't recognize it. On data set 2 of COPD abstracts, we can notice this. So this is what was bugging me before. Now we managed to conflate that in a single term representative. The same here, COPD exacerbations, 6, 7 different variants grouped together. Here they were broken down into 2 separate term representatives. Again, if you look at the most frequent terms, we can say, okay, COPD is still ranked number 1, but in all other cases, the ranking improved, and again, look at the recall. So terms that we were not recognizing before now are highly ranked terms. Data set 3, this is interesting. So this is COPD blogs. So obviously all they talk about is COPD. Here, we didn't even register that. Here, of course, it's a topic number 1. So COPD, all they talk about. So it's now ranked as term number 1. So we can see here, we didn't have too many acronyms, we only recognized 2. But recognition of these 2 acronyms helped us recognize 2 new multi-word terms. One is obviously the most important one, and this equally, ranked number 13. These are hospital discharge summaries. Again, nothing interesting here, but again, the same story, ranking improved. And this one is much more interesting because it changed the output quite considerably. So we have 3 terms here, and if you look at these acronyms, and we only managed to pull 4. These are implicit acronyms, by the way, so they were not defined in an MRI report. We can see that 2 of them were not even recognized before. So such important things like anterior cruciate ligament and posterior cruciate ligament were not pulled out before. Now they're ranked number 2 and number 5. So in conclusion, obviously the numbers tell us that recall improves significantly with the inclusion of acronyms. Term completion improves as well. So we can now text mine the whole corpus, referring to these to concepts as latent variables, even though we don't know what they are, but at least we know that we refer to the same thing. So that has got implication on any sort of statistical analysis, models, methods based on statistical analysis like topic modeling. And ranking improves, again with implications for any sort of content analysis where you want to consider the importance of terms for the discourse that you're describing. Thank you very much for your attention. I'll answer questions now.